Okay, welcome back everyone from the coffee break. It's my pleasure to introduce the second speaker for this conference, Adèle Bourgeois from the University of Ottawa, and she will tell us about restricting representations via restricting G-data and KIN-U types.
Thank you. So this is my first time giving an online conference, so this is very exciting. And yeah, so today I'll be talking about some of the results that are part of my PhD thesis. So the notation in this talk, we're going to let bold G denote a reductive group, which is defined over some p-adic field F, and capital G is going to be the F points of this p-adic group. And then bold H is going to be a reductive F subgroup of bold G that contains the derived subgroup of bold G. And so the goal in this talk is to take an irreducible representation pi of our p-adic group G and study its restriction to this particular p-adic group H. And we will be assuming a few underlying hypotheses. For instance, we assume that the reductive group G splits over a tamely ramified extension of F, and that the residual characteristic of F does not divide the order of the Weyl group of G. So for irreducible representations of p-adic groups, we have Jacques' subrepresentation theorem, which splits them into two categories. So we have the first category, which are the supercuspidals, and the second category, which are all the irreducibles that appear as components of a parabolic induction of a supercuspidal. So this talk is going to be divided into these two sections. So we're going to start by looking at the irreducible representations, which are supercuspidal. And for these, we can obtain them via the JKU construction. And what the JKU construction does is it starts with a G-datum that I'll denote by psi. From this G-datum, we can construct an open compact mod center group that we denote by KD. And we also construct some representation kappa G psi here, which is an irreducible representation of KD. And when we induce this representation to the p-adic group G, then we obtain a representation that is irreducible supercuspidal. And with the underlying hypothesis that we have on the residual characteristic of F, Finson showed that U's construction here is actually exhaustive. So all the irreducible supercuspidal representations, they come from this kind of construction. So as a first observation, if I start with a supercuspidal representation of G, so this pi G psi, and I restrict it to the subgroup H, this is going to decompose as a finite direct sum of irreducible supercuspidal representations of H. So by the exhaustion, all of these representations pi I, they are constructed from some H data psi I. So there's a first natural question here of what is the relationship between our initial G datum here and the data psi I that construct the components that appear in our restriction. Okay, so in order to establish this kind of relationship, we need to go over what a datum is. So a datum consists of a 5-tuple, so it has 5 elements, and each of these elements, they satisfy some interrelated conditions. So we're just going to briefly go over these conditions, but they are very specific to the structure theory of p-adic groups, so it's okay if some of the words here aren't super familiar. So the first element we have in our datum is what we call a tamely ramified twisted Levy sequence. So this G0 is a twisted Levy sequence that is contained in the twisted Levy subgroup that is contained in the twisted Levy G1, and so on. And GD is equal to our reductive group G. The second element is a point Y, which comes from the Bourgeois building of our p-adic group. The element rho here is some irreducible representation of a subgroup that we'll call K0. So this subgroup is indexed by the point of the building that we chose, and it induces to a supercuspidal representation of depth 0. R here is just a sequence of increasing numbers, and this phi here is a sequence of generic characters. So this phi 0 is going to be a generic character of G0, and it has depth R0. And all of the last character is allowed to be trivial. So if the last character is is non-trivial, it has to have the maximal depth of the sequence, or we can allow this character to be trivial. Okay, so from this G-datum, the natural thing that we could do to get it down to an H-datum is just to restrict each of the parts to the analogs in H. So we start with our twisted Levy sequence in G, and we're just going to take each of the subgroups, intersect it with the reductive group H. For our representation rho, well, we're going to take the restriction of rho to this H0 square bracket. So this is the H analog in the group that we had for rho. And so we're just going to restrict it and take any irreducible component of that. And for our characters, we're just going to restrict each character down to the subgroup in H. And because of this last axiom on the depth, so we need to look at the depth of our last character here. So if this depth is bigger than RD minus 1, so bigger than the depth of this guy, then we can define our sequence, and we know our last character will have the highest possible depth. Or if the depth is smaller than our before last guy, we need to fold it in with the phi d minus 1. And that's just to make sure that our axiom for the datum is satisfied. And then when we take all of these restricted elements and put them together, that forms an H-datum. So getting back to our supercuspidal representation, our pi g psi was constructed from this 5-tuple, and we just saw that this 5-tuple can be restricted in a very natural way to produce H-data. So we have an H-datum here for every component of rho, of the restriction of rho. And each of these H-data produces a supercuspidal representation of H. So what we would expect here is that the supercuspidals that we obtain on the bottom here, that they would be components of the restriction of pi g psi to H. And so this is a very natural conclusion to make, but in order to show this, we need to go into all the technicalities of the JKU construction, which turns out to be a pretty non-trivial task, but I'll just kind of give you a summary of what goes on. So the JKU construction, how it works, is it starts with our sequence of characters. Now, instead of looking at, the phi I to be the character of GI, I'm going to restrict it down to a compact mod center subgroup. So the K0, this was the subgroup that appeared in the datum. The KD is the inducing subgroup, and all of these KIs in between, they're compact mod, the center of the group that they belong to. And so we start with our phi I's, and the first step of the JKU construction is to extend these characters to representations of the next compact mod center subgroup. So we're going to take the phi 0, extend it from K0 to K1. The phi 1 will get extended from K1 to K2, and so on. And this extension process, Heisenberg groups come into play, and we have Weil representation. So it can get a little messy, but we can get the extension. And after we have all of these extensions, we just inflate these representations to the inducing subgroup KD. So inflation is essentially just making our representation trivial on the complement. And then our representation kappa is just going to be the tensor of all of these representations that we've constructed. And the kappa minus 1, I don't have it on the slide here, but this is just the inflation of rho, which was a part of our initial datum. And then this kappa gets induced to produce the supercuspidal. So all of this notation that we have, so we had our inflation of rho, we have our extension and inflation of the phi I, we have analogous notation for the H data. So my rho here was restricted to some direct sum decomposition of rho L, and same here, my phi I gets restricted to some phi IH, and this phi IH I can extend and inflate using the JKU method. And what's nice with the steps of the JKU construction is that it ends up commuting with restriction. And because it commutes with restriction, then we can show that when we take our kappa g psi and restrict it to the inducing subgroup that's in H, that it'll decompose as a direct sum of the kappa H psi L's. So the kappa H psi L would be the inducing representation obtained from the data. And then we go and compute directly the restriction of this pi g psi to H by applying a Mackey decomposition formula. And so that's where this set of coset representatives pops up. So this is from the Mackey formula. Okay, so for the irreducible supercuspidal representations, starting from the datum and restricting the datum, we do get a really nice full description of our restriction. So let's see what we can do with the other kinds of irreducible representations. So those that are not supercuspidal. All right, so in this case, in the case of the supercuspidal, we had Montener's theorem. So we know that our representations, they are all induced from some compact mod center subgroup. But when we're looking at non-supercuspidal representations, we don't have this kind of analog. So instead, we're going to turn to the theory of types to try to get some information about the restriction. So to talk about what a type is, first, we need to know the Bernstein decomposition. So the Bernstein decomposition takes the category of smooth complex representations of G, so this RG, and it says that it can be written as a direct product of some subcategories, which are indexed by some pairs M sigma. So M is a Levy subgroup of G. Sigma is a supercuspidal representation of M. These pairs are subject to some sort of equivalence relation. And so we can have a decomposition of this category of representations which are indexed by these pairs. So if we take J to be a compact open subgroup of G and lambda to be a smooth irreducible representation of J, then we say that the pair J lambda is going to be an S type if for every irreducible representation pi of G, we have that this relationship holds. So our pi is going to belong to the Bernstein block indexed by S if and only if the restriction of pi to J contains the representation lambda. And we will say that an irreducible smooth representation pi of G contains a type if there exists some S type J lambda such that when we restrict pi to J, it contains this lambda. So essentially types, they allow us to describe representations via representations of compact groups. Okay, so Kim and Yu, they described a construction of types. And this construction of types is actually completely analogous to Yu's construction for supercuspidal representations. So this construction of types, it starts with what I'm going to refer to as a type-datum. So we'll denote this by sigma. And from this type-datum, we construct an open compact subgroup J and some representation lambda G sigma, which is an irreducible representation of J. And the construction of this lambda is completely analogous to the construction of kappa that we had in the JKU construction. And then this pair J and lambda G sigma is a Kim-Yu type. And again, under our underlying assumption on the residual characteristic of F, Finson showed that every irreducible representation pi of G actually contains a Kim-Yu type. So, okay, so because this construction of types is essentially the same as the construction of the supercuspidal representations, our ideas of restricting data, they will just kind of get transferred over into this setting. So our type datum, again, is a 5-tuple. And they all each element in this 5-tuple again satisfies some interrelated conditions, and these conditions are very similar to the ones of a G-datum from before. So our G here is again a twisted, tamely ramified twisted Levy sequence, and here we just add M0 to be a Levy subgroup of G0. Again, our Y is some point in our Brouhat-Tietz building, and here this I is an embedding of buildings. So the building of M0 has to be embedded in the building of G0. So we need to specify this kind of inclusion. Rho here is going to be an irreducible representation of M0Y. So in the JKU construction, we had a square bracket here. And again, R is just the sequence of increasing numbers, and our sequence of characters is defined exactly in the same way as we had before. So if we want to talk about a restriction of type datum, well, we're going to do exactly the same thing as we did for the G-datum. So we're just going to take our twisted levy and our levy M0, restrict that with H to produce a twisted levy sequence in H and some levy subgroup of H0. Rho again is going to be restricted to the analog subgroup that's in H, and we're just going to take any irreducible component of that. And our restriction of characters is done exactly in the same way. So once we do this kind of restriction process, then we put all of these 5 ingredients back together and we have a type datum for H. And again, we're going to have a type datum for H. So each irreducible component of Rho is going to produce one of these type data. Okay, so starting again from our Kim-U type here, so we know that this Kim-U type was obtained from some type datum for G. And then by what proceeds on the previous slide, we do have type data for H that we are able to construct by this natural restriction. And these type data are going to, again, produce Kim-U types. And because this lambda G and these lambda H, those are completely analogous to the kappa G and the kappa H that we had before, we have a decomposition formula for the restriction of our lambda G sigma to our compact subgroup JH that's inside of H. And it's written as a direct sum of all of the lambda H's that were produced from the restricted type data. So here we're talking about the type. So what does that tell us about the actual representations? Well, if we have pi as an irreducible representation of G, so we know that this pi contains a Kim-U type. So we have a pair J lambda, which is contained inside this pi. And so that means that all of the types that we obtain from our restriction, those are going to be contained in our restriction of pi to H. But now the one downfall with this is that the theory of types does not give a direct correspondence with representations. So you can have the same type that belongs in different representations. So at this stage, so we do have information about the restriction of pi to H, but there are still lots of open problems to try and figure out if we could get a really nice description of what this decomposition of pi of H would be. So maybe, hopefully we could get something as nice as we had for the supercuspidal representations, but that is not quite clear just yet. So thank you, that's all I have.
Thank you very much. Oh, I see clap clap in the chat. Awesome. Okay, we let people clap a bit. If you can see the chat, you enjoy the clapping. And meanwhile, if someone has a question, feel free to raise already your hand or to post a question. Oh, Lauren raised his hand. Okay. Lauren, do you want to ask the question?
There we go. I think I'm audible now. I think you mentioned, I missed the definition of this. I think you mentioned that the depth of phi d might drop when you restrict to the derived group or raise or whatever the depth does. Yes. But this doesn't happen for the other characters?
No, so what's nice is that, yeah, so I'll just get back to this slide here. So what's nice is that the genericity, so these characters phi I, those are all, they satisfy this genericity condition, and the last character phi d doesn't have this kind of generic notion because GD is the last one. So when you restrict the generic character to its H analog, it actually remains generic of the same depth. So we don't need to worry about that.
Thank you.
Thanks. There's another raised hand, but I can't find it right now. Oh, David Bow. Okay, I'm unmuting you.
Hello.
Hi.
So I had a question about the point in the building. So when you restrict the representation rho, you restricted it at the point Y. So is there an assumption that Y is in the building of H included inside the building of G?
Yeah, so I guess in this case, when we're looking at the supercuspidal, the point Y, we might as well assume that it's in the reduced building because the Moy-Prasad filtration subgroup, so our construction relies on these filtration subgroups like GI, Y, RI, or whatever. And regardless of whether we're in the reduced building or if we're in the extended building, we're gonna still be in the same facet. So it won't change the Moy-Prasad filtration subgroups. So essentially what we're doing is we're saying we have our point Y, which is in the extended building, and then we kind of projected it down into the reduced building, and we took that to do our Moy-Prasad filtration subgroups.
Got it. Thanks.
Thanks. I see one more raised hand by Hadi Asian. I unmuted you. I hope you can talk.
Yes, sorry. Can you hear me now?
Yes.
I have a question about the supercuspidal case. So how can you make sure that the decomposition exhausts, and what about multiplicities? You can have multiplicity in the restriction.
Right, so in this restriction here, so this formula here, that's what you're referring to? What can we say about multiplicity here?
Yeah, and also how can you make sure that you've got all of the types that show, I mean, that like all of the types for the representations in the restriction? In other words, why is that there is no other type which didn't come from the restriction above? Right,
so there's this whole notion of G equivalence that kind of is lurking in the background of these data. So you can have one supercuspidal representation that can be represented by, I guess, different data, but there will be some sort of G equivalence relation between these two data. But this formula really just comes from a direct Mackey decomposition and using the fact that we have this really nice description of our kappa G here. And if we want to talk about the multiplicity in here, using, again, this notion of G equivalence, we can actually show that there is the only source of multiplicity is really inside this direct sum over L. So if we have two different elements coming from this set C, our representations won't be isomorphic. So if I have a T here and I have an S, those two representations can't be isomorphic because of this notion of G equivalence.
Okay, thank you.
Thank you very much. I think we should stop here and thank Adèle again. And everyone who has questions can join Adèle afterwards. Adèle is hosting a Zoom room. So feel free to ask her tons of questions there during lunch or dinner, depending on what time zone you're in. I see a lot of clapping. That's great.